Manu?
Yes, sir.
Yeah, so any specific topic you want to discuss today in today's session?
So this quick select and fast select.
Okay, quick select and fast select. Okay, okay, fine. Others, Hemant, Nidhi, Roli, Bhavya, Paramita, Sandeep. Okay.
The median of medians.
MOM. Okay, okay, fine. Others. Okay.
So regarding the graded question, it's becoming difficult to find out whether the algorithm is working or it's not working due to timeouts, because although I'm getting all the pass public sets and also one or two private sets, but
So, which person you are talking about?
so graded questions 1, 2, 3, 4, all 4.
All. Okay.
So we
So,
don't, because of timeouts, we are getting less.
no, if we are asking any time complexity,
all of them there's time.
Yeah, all of them. Okay, so first question have your time set for this question. Okay, and login time. This is also okay. Minimum distance. So, okay, so should run be all of the login time list. This is MOM. Okay, on time. So
I get an error at least telling that this is due to time, because I mean.
Okay. Yeah, currently in private test case, you cannot see the reason why your test case is failing. Okay. So what we can do, we will ask the operational team, because this is not, this things cannot be changed immediately.
Okay.
Okay. So just provide the efficient code and just check the corner case, all corner case things. If you are thinking that your code is efficient and you are performing the efficient algorithm, so just check the all corner case locally. Okay. Then you can find the things. Okay. Okay, so topic. So quick select, I'm starting from the, so in the last session I have discussed till integer multiplication thing, logist pair things I have already discussed, and quick select and fast select. Yeah, so this one. So basically what is the quick select and fast select? Here we are finding out the kth smallest or maybe kth the largest element in our unsorted list. Okay, so in unsorted list, how you can find the kth smallest or kth largest element? So if you are using naive approach, so for example, if we have a list, so here we are talking about kth largest. So for example, if we have a list, this is an unsorted list, like 6, 1, 4, 8, 3, 9, 2, 1. For example, I'm not repeating like this. Okay, this is an unsorted list, and I want to ask that what is the fourth smallest element? So first smallest is this one, 1. Okay, so I am asking that what is the fourth smallest element? I don't know what is the element, and elements are not in the sorted order. So what we will perform in the naive approach, we will compare the element one by one, and we will find out this smallest element. So first we will find out the first smallest element. So we will compare. So we will select that. For example, we will assume that first element is the smallest element. Then we will compare this element by this compare this element with the each element to find the smallest element in one loop. So by matching all these elements with these elements, we can find the first smallest element. After that, we can separate this element and then we will repeat the process again, same process again. So we have to repeat this process 4 times. If we are finding out the fourth smallest element, so we have to repeat this process 4 times. So first, in first process, we will find the first smallest, then second smallest, then third smallest, then fourth smallest. So this is the naive approach when we are comparing each element to others, all others remaining elements. Then we are finding out the results. So this process basically a n square time process. Other we can perform the second approach is if we sort this data. So for example, if we sort this data, and then after that we can return the fourth element from the starting. So that will be the fourth smallest element. So that will also take n log n time, because currently we have learned 4 type of sorting algorithms. So selection sort, insertion sort, merge sort, and quick sort. So where the merge sort and quick sort provide the n log n complexity to sort the algorithms. Okay, so for example, if we want to find out the kth smallest element, so then we will sort these elements first. So it will take n log n time. Okay, and after that we will return the fourth element in the sorted list. That will also a solution, but the complexity of this solution is also a n log n. So how we can perform this finding the kth smallest and kth largest in more efficiently? So there is a way. So we can apply the divide and conquer approach on this list. So we will use the quick sort concept. Basically, we will use the quick sort concept where we use the partition things. If you remember this, in quick sort algorithm, we have learned the partition function. Basically, what partition are doing. So we will use the same approach to find out the kth smallest element. So what we will do, we will so this is the actually unsorted list where we are finding out the kth smallest. We will take this list as an input, and we will apply the partition process on this input list. Okay, so for example, if we are applying the partition process on this input list, so what the partition will do? So partition will take, so for example, we are assuming that in partition function, we are selecting the first element as a pivot element. After that, we will compare each element with the pivot element, and after completion of the partition function, we will return the actual position of the pivot element. Okay, so for example, we are applying the partition function on this input list first. Input list. So we will select that 6 is a pivot element. Okay, 6 is a pivot element, and then we will apply the partition process. We will we will go through the each element, and then we will compare that what are the elements which are less than this pivot, and what are the elements which are greater than this pivot. So for example, after completion of the partition process, so we are assuming that the all smallest element of the pivot compared to the pivot elements will come before, and so I'm assuming that this 4, 3, and then 2. Okay, so these are the smallest element. These are the smaller element compared to this 6, and then 6 element will come here, and after that the all greater element, one more is remaining. 5 is also remaining. So 5. Okay. Yeah, so 1, 4, 3, 2, 5, these all elements are smaller than this 6. Then 6 will come. After that, all greater element will come this pivot element. So 8 and 9, only 2 elements are there. Okay, so partition function basically shifted the pivot element at the actual position after the sorting elements. So what is the purpose of partition function is that it actually find out the actual position of pivot element in the sorted list. So this 6, so for this 6, 0, 1, 2, 3, 4, 5, 6, 7, these are the index of the list. And so after partition process, this 6 will are coming at the 5th index. So if you sort the list, so for this is an input list, if you sort this input list, so this 6 will come at the fifth index. Okay, so we can say that after completion of this partition process, so this 6 came at the actual position. So we can say that so this partition function will return the actual position of the pivot. So this partition function will return the fifth index. Okay, this is the position of our pivot 6. Then what it is representing and what are the complexity of partition? So partition complexity is order of n. Okay, in partition function, basically what we will do, we will just read each element and compare with our pivot element. If some swapping is required, then we perform the swapping operation. Then, so what it is representing, this position, what it is representing, we can say that this is a this is an index actually. So we will add one in this index, and we can see that this is a sixth smallest element. Okay, so in sorted list, this is coming at the sixth position, not the index, sixth position. So we can say that this is the sixth smallest element. And what, for example, if we are finding out k equal to fourth smallest element. Okay, so one partition process, we have our position is returned sixth position. Okay, of the pivot position. So we can say that this 6 is a sixth smallest element. So what we will do, we will discard this part completely, or we will discard this part completely. Okay, because we are finding a fourth smallest element, and in the one partition process we get the sixth smallest element. So definitely fourth smallest element will come before this sixth smallest element. So we will discard completely after that. After that, we will apply the partition process on this part. Okay, same process we will apply on this first half part before the pivot element. Now we will select again what is the partition. So we will select, for example, this is a pivot element, and then we will perform the partition process. So this is a first element. After performing partition function, so it will come the same like this 4 3 2 5. Okay, now this is the zero index. So this partition function will return the zero index of the pivot position 1, and we can say that this is a first smallest element. So but still we are asking the fourth smallest element. So definitely fourth smallest element will come after this first smallest element. So we will apply our partition process on this part. Okay, now we will consider that this is our pivot element. So now this is in our input list. So this is the 0 index 1 2 3. Okay, so we will apply the partition process on this part, and then we will compare all the elements, and all smallest element will come before, like this 3 2 and then 4 and 5. Okay, so so now, okay, so input list is the same. So for this is the 0 index, this is 1 2 3 4. The index will remain the same. So now what is the pivot position after that? So we will select this pivot element, and okay, so this is the fourth, and fourth that come at here. Okay, now so this is the 0, and this is 1 2 3. Okay, now pivot at come at the correct position. So this is the third index. Our partition function will return the position index of this 4. This is 3, or we can say that this is a fourth smallest element. So we will get our answer. That means 4 value is a fourth smallest element in our list. So you can see that every time we are discarding a approx half part. So if our pivot element is coming in between the list, so definitely we will discard half part of our list for searching the next further. For searching the further list, we will discard the half part of the region. So you can see that in the partition function is taking n time. Okay, and every time we are performing n operation. So if we are starting with the n, so if we can if we can write the recurrence relation for that, so we can write the recurrence relation like this: Tn. This is the main problem. Every time what we are doing, we are just calling T Oh, sorry. Discarding t n by 2, and every time we are our total operation are performing is big O n. Okay, so we are calling our partition function recursively on the half part of the area of the list. Okay, so that means every time we are reducing the our searching area. So if you can draw the tree of this, so for example, if you can draw the tree, so initially this is a tn, okay, and that this part is called the fn. Okay, so I'm just explaining using the recurrence tree what will be the complexity of this. So this is a fn part, and fn part is a n for the initially. So because partition we are applying the partition function on n element initially, so it will take n time in the first level. In the second level we are discarding half of the element for the searching, so that means we are performing our operation t n by 2. So that means f this part fn part will also reduce, so it will become a n by 2 operation. Okay, our partition function will perform on n by 2 elements that at that level. Okay, so here this initially this is n, in the next level this is n by 2, and same for next. So we will perform n by 4. Now this is n, this will become n by 4, and that is anytime we will reach at one value. Okay, we will find the answer. So every time our total number of operation are reducing at each level, our operation are reducing. So initially that are n, then next time n plus 2, then next time n plus 4 plus dot 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 1. So according to the recurrence tree concept, if our number of operation are decreasing fractionally, so we can directly retain our complexity equal to big O fn. Okay, so initially our fn was big O n, so we can directly retain as our complexity n. Okay, so if we will perform this divide and conquer approach to searching the kth smallest and kth largest element, so we can find this information in order of big O n time, okay, we can find out this. But what happened, currently I'm explaining the quick select concept. Okay, so quick select, basically what happened in the worst case thing. So similar to quick sort. So in the quick sort case, if our pivot element come at the corner every time, okay, so we will perform our quick select algorithm on the n-1 element each time. So for example, if we are starting from tn, okay, initially we are performing our quick select algorithm on n element, and our pivot element come at the first position, right? So we will apply the quick sort algorithm on n-1 element. So that means that in the next level it will perform on n-1. Same things, if we will repeat these things, so say once again our pivot element come at the corners, so we will perform our quick sort again on our n-1 element. So then that means it will reduce by 1. Okay, so like this, every time we are performing our quick sort algorithm on n-1 element. So initially this is a this is n, this is n2, yeah, this is n-1, this is n-2, like this. So our series will be like this. So we can add this series. So n equal to n-1 plus n-2, like this. So we will get the complexity or total of complexity n square. Okay, we have already seen this type of series in the selection sort, insertion sort. So this is the worst case of quick sort also. Okay, so these are the things and how we can improve this quick select things and also quick sort things, how we can improve. So there is one algorithm MOM discussed in the lectures. So now you can see the code here. What we explain this thing. So quick select code, if you can see. So this is the quick sort we are calling. So we can just go. My VS code is visible?
No.
Oh, okay, one second. Now it is visible?
Yes, sir.
Yes, sir.
Yeah, so this is a quick select algorithm. So we can run this step by steps. So you can see this is the, basically we are calling this quick select on this list 5 3 7 2 1. We can increase more. So like 6 8 10, 13, and 4. Like this, okay. And initial index is 0, and what are the total number of elements is 1 2 3 4 5 6 7 8 9 10. Okay, so this is the 10, and we are asking to find out the, for example, fourth smallest element in this list. So I'm just changing this element by 30. What are the fourth smallest element now? And I'm just putting the one break. Okay. We are calling this function quick select algorithm. We are passing the one unsorted input list. This is the initial index 0, and this is the total number of element. That means last index plus 1, and this is the kth value which we are finding out. And after that, after getting this, if the element k is less than 1 or k is greater than n minus 1, return none. That means if we are passing kth value is less than 1, that means there is no meaning for less than 1. There's no, we cannot ask the zeroth element, what is the zeroth smallest element. And same things, if we are asking the k is greater than r minus l, that means if we are, for example, if we have a 10 total elements, and we will ask that what are the 15th smallest element. So there is no and elements are less, and we cannot ask the larger value. So because of that, we have taken this condition here, and then we will return none. And in the second case, we are selecting here pivot element as the first element of the list. So this L is representing basically the first index. So this is L, and we are just assigning this lower and upper value. This is basically a partition process. You have already seen in the this process in the quick sort algorithms. So this is actually the same partition process we are using here in the quick select algorithms. Okay. So we will perform this pivot partition process, and this partition process will return the index of our pivot element here. Okay, so this lower line, these things, and we will check after returning this, after finding out the actual position of the pivot element. We will check that if k is less than equal to lower line, this is the index of here we are reducing this lower things. Okay, we are checking that if k is less than equal to lower line, then that means we will discard the upper searching part. That means our pivot element, for example, is coming at the 6th position, and we are asking the 4th position. So definitely k will become a 4, and this lower line will become a 6, and then we will discard the upper part after the 6th index. So we will apply this quick select algorithm on the lower part. So here we are assigning the low, we are changing this upper index of our algorithms. Okay, so we are applying this quick select algorithm on the lower part, and this is the second condition, second situation. If our k is equal to lower line plus 1, actually this lower line is a index of our pivot element, and this is plus 1 is representing a position. Okay, so if our k is equal to this position, that means that is the answer. That we will directly return the element k lower. So this is a correct answer. Otherwise, the remaining condition, if our k is greater than the lower len, then we will call the quick select algorithm on the upper part and we will discard the lower part here. Okay, so this is the quick select algorithm which I explained in the previous example, and it will return the answer. Okay,
Sir, why lower len equal to lower minus 1, sir?
actually
I
lower.
didn't got that part.
Okay, we have to see the whole partition process. So what is the lower actually in last time? Actually, we reduce this lower here, lower minus 1. Okay, 1 second.
Sir,
Okay,
this is lower minus L, I think.
Yeah, this is, oh, okay, this is lower minus L, not a 1.
Sir,
Lower,
why is that? I didn't get that part, sir. The 16th number line, sir.
okay, okay. So in partition, what are our partition function is, what is the lower value? Lower value, okay, so I'm just running it and check the what are the coming in this lower value. Okay. So yeah, initially we have a list, so you can see the input list, and this is the k value. L value, so k value is 4, L value is 0, R value is 10. Okay, we will perform our partition process now, and after completion of this process, we'll check that what we are getting in the lower. Okay, yeah. So you can see the we are getting lower equal to 6 here. Our pivot element was 50 in the first case. So 50. Pivot is change. Okay, so this is the actual list. We have performed operation. So this is the input. This is our input list. We have selected this 50 as a pivot element. Okay, and after that, in the partition process, we find out the what is the index of this pivot element. So index of this pivot element is 6. You can see this is the list after performing the partition process. So you can check the what is the index of this 50 now. So 0, 1, 2, 3, 4, 5, 6. Okay, that means this lower is containing the value of index of pivot element after the after performing the partition process. Okay, after that, here we are just checking lower len equal to low. So this process actually we can okay, lower len equal to lower minus L. So L is our 0. So same value will be we will get in our lower len field. So now lower len, you can see that is the same. And okay, yeah, lower len minus L.
So why are subtracting L from the lower, sir?
Actually, when we will call the recursive part, so actually at that time this L and this upper value will be changed, will become changed. At that time we have to check that what will be the position or what are the correct index for that. So for example, this lower len. So okay, so now I'm performing again. What is the next thing? Now this is the next second partition call. Here we are getting this k, yeah, L is equal to 0, but R equal to 6. Here L is the same. So we will not, this things will not reflect here also. So wait for the others. Yeah, now this time our L values become changed. Okay, so actually here we are passing this L list and we are changing the index. Now our this time our calling list index is 1. That means we are performing our partition process from 1 to 6 index. Okay, so here L equal to 1 and R equal to 6. So that means we are performing our partition process from 30 to this 50 element. At that time, we will so here for getting the actual position from the first element, we are reducing this L value. Otherwise, if we will not perform these things, then we will maybe the index or position value will become changed. So, for example, here k value equal to 3. Okay, so now k is also reduced. K is okay. So we can skip this part, I think, okay, because here we are changing the k value. So I think it is not required. We can pass the k value and yes. Yeah. Okay.
Sir, can you take this example and explain in rough what
Yeah,
is
yeah, so
happening
I have-
one by one in the stepwise?
Yeah.
Like this
explain
line number
with the
16 to
example.
21, 22.
Yeah. You want to explain the coding line number 16 to
16 to 22. This stuff, sir, like what is happening here with this?
okay.
Like that part is pretty clear because that is quick sort. But after that thing,
So this is the initial things. So after first partition, actually we are reducing the kth value also. Initially we are asking the fourth smallest element. Okay, so k equal to 4. After first process, we in the first process we select this pivot element and we check that what will be the list. Okay, we have to check that from here. We have to perform completely. So stop this process. So in the first partition, so now first partition is completed. We got this list. This cannot be copied. Okay. So 4, 30, 20. Putting down this 4, 30, 20, 10, 10, 13. Fifty, 70, 60, 70, 60, and 80. Yeah. So initially we perform first partition process. So after that we got this. So this index is basically 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 to 9. Okay. So what is the pivot position is this 6 index. This 6. Okay, so 0. Yeah. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So after partition process, we got the position index of the pivot elements. This is the 6. Index of pivot 50 equal to 6. Okay. Now here we are just using this process. Lower len equal to lower minus L. So here actually we are just finding out the index from the 0th position. From the 0th position means what are the index from the 0th position. So lower len equal to index minus L. So L is the initially, that is the 0, this thing 0. So 0, it will become a 6. That means this is the index of this list after the sorting. But every time when we are sometimes we will reduce this list when we are calling again. We are reducing the size of the list. So at that time we have to check that what are the index of the initial of the actual list. What are the index from the 0th position of in the actual list. So because of that, we are just calculating this lower len equal to index minus 0. Okay, we will see in the next iteration. So initial this actually this value is representing that this 6 index is in the actual list. That means we can see that our 50 is the 6th smallest element in the actual list. Okay, in the next iteration, so what we will do, what we will perform the, so we are finding out the 4th smallest element, and this is our 6, that means we can say that this is 0. Okay, starting from the 0, this is a 7th smallest element. Okay, so we are getting the 7th smallest element from this partition process, and we are finding out the 4th smallest. So definitely we will discard this part. We will discard this part completely, and we will perform our quicksort algorithm on this part. Okay, so now here our L, so we will calling our quicksort algorithm on that part, and now our list will become a 4, 30, 20, 10, 10. List will remain the same, but we will pass the index. Okay, so so list will remain the same, and we will pass the index, first index as a 0, because this index will remain the same, and the upper index we will change. Now this will become a lower minus, so this is the last lower len minus 1, that means 5. That means we are performing the quick select algorithm on that part only. So now you can if you perform these things, so in this part this recursive call will be performed. You can perform this action. Now this part will be performed. Now you can see what are the L value and what are the R value. Okay, we are also considering the pivot element for the searching. We can also reduce these things. Okay, so now this time 0 is the initial index and 6 is the last index. That means in searching area, we are also considering this 50 for the next term. So that means next time 4, 30, 20, and 10, 10, 30, and we are taking one larger value. Okay, then fine. Yeah, we are searching in this process, and we are taking L equal to 0, this is the initial, and we are taking R is the last index plus 1. The last index is 5, and then 5 plus 1 is 6. Okay, so you can see these things here, and K will remain the same. Now in the next iteration, now we will check. So now our first element is 4. Okay, so we will select this 4 element as a pivot element, and then we will perform the partition algorithms again. Okay, so now upper lower equal to 0. Okay, in the case, so pivot position will remain the same. That means our pivot element 4, and after the sorting it will come at the same position. Now this is a pivot element, and 30, 20, 10, 10, and 30. Now we will perform our quick select here. So you can see there is a element we have a discard, but it will consider from the first position in the you can see that this will consider. So we are saying that 4th smallest element. Okay, K equal to 4th smallest element. So 4th smallest element coming from the first element in the actual list, and here we are discarding the element before that. So we are discarding one element before that. So definitely we will reduce our K value now, because we will perform the quick select algorithm on that part. If we find out that this is a 3rd smallest element in this list. Okay, in this list if we found that this is a 3rd smallest element, that means if consider this one, this is a 4th smallest element. Okay, so in this recursive call list, this 10 is a 3rd smallest element, but if we consider this 4, then we will add the one more in our kth value, so that will become a fourth smallest element. So because of that, when we are discarding the lower part, so we will reduce our k value by how many elements we are discarding from before. Okay, so here we are discarding one element before that. So that means we will reduce our k by this length of this discarding part. So you can see that in the in this condition, in this condition, we are reducing this k minus lower length plus 1 things. Okay, that this lower length plus 1 is representing the how many elements we are discarding before that. So one element we are discarding, that means it will also, so we will reduce our k value. Yeah. Okay, because we are discarding before that. That will consider in our kth smallest element value, because we will finally return the kth smallest value in the complete list. If we are discarding any part, so before that will also consider. Okay, so we cannot return these things. So we can here, for example, if we will not reduce the k value, that means we cannot say that this and for example in this list we are getting this is the fourth smallest element. So we cannot return this answer, because 4 is also coming before this. After sorting, this 4 will also come in this list. So this will list become like this 10 10 20 30 sorry 10 10 30 20 30. So after sorting, this 10 cannot be a fourth smallest element. So because of that, we are reducing this kth value in every steps when we are discarding the lower part. So how many number of elements we are discarding, we are reducing from the kth this here. So when we will perform that, so you can see we are going here, and at that time our k value will be reduced, and because L value is 1, that means we are performing our quick select algorithm now 30 20 10 10, and R is 6. Okay, so R is 6, that means we are going till here now. Yes, okay, we will perform our so what is the input list is now 30 20 10 10 30 30 20 10 10 and 30. Okay, so we will perform our quick select algorithm here, but this is at first index. Okay, this is second index, third, fourth, 5. Okay, so in the recursive call, we are just passing that L equal to 1. Okay, and there is one element we have discarded. So after sorting, this will come before this part. Okay, this 4 will come before this part after sorting. So because of that, we are reducing now k here. So R will remain the same 6, and k we are reducing that 4 minus how many number of we are discarding before that is 1. It will be coming 3. That means now we will find out the third smallest element in this part, because one smallest element already is there. Okay, now we perform same things. Now 30 is a pivot element. Now we find out what is the position of the pivot element in this list. So we will perform repeat this of the pivot element partition process here. Yeah. So okay. Now 30 is the pivot, and the lower lane, and what is the lower lane? So this lower is a actual index 5. So now after sorting, you can see that after sorting, this 4 is coming before this sorting part. So 13 20 10 10 30. Okay, so if you see this part of the list, so when we are selecting this as a pivot, So after partition process, this element will come at the last position because this is a greatest element in this part. So you can see 13, 20. So 13, 20, 10, 10, and 30. So all elements are coming before are the smaller element, this 30. Okay, and this is coming at the 5th index. So we can say that this is a 5th smallest element. So we will perform our quick select algorithm on now this part once again. Still we are not reaching at the actual result. Now we will perform our quick select algorithm. Now this is a first index, and we will, this is a 2, 3, 4. Now our L value will become, here we are discarding the previous part. Okay, so there is no requirement because this 5th largest element, so there is no requirement of this 5th largest element because we are searching a 4th largest smallest element. So we can discard this thing. So we will apply this quick select algorithm on before this part. So now L will remain the 1 and R will become a 5. 4 plus 1, 5. And K will remain the same, 3. Last time we have reduced it. You can see. So you can see the now L is 1 and R is 5. And we have selected pivot equal to 13 now. And we will perform all the operations of partition here. Now we will get this information. Yeah, now 13 will come at the, now our list will become 4, 10, 10. So 10, 10, 13, 20. So 4 we have already initial. Now 13, 10, no, 10, 10, 13, 20. Okay. So this is at 0 index, and now we are coming here. So 1, 2, 3, 4. Okay. So now the lower is a 3. Then our pivot element come at the this 3 index. Okay. Now we will check that what is the position. You can see lower lane minus equal to lower minus 1. So lower equal to 3, lower lane equal to become 2. Now this first condition, K is less than equal to lower lane. So this is not true because K equal to 3 and lower lane equal to 2. Okay, so this will, yeah, now check. So K equal to lower lane plus 1. So yes, 2 plus 1 equal to 3. So now this condition will become true, and we will return the answer from here. Okay, so now this is the last step of the quick sort, and we will return this answer 13. So here K value is a 3, and we will check that now this value will become equal to this one, third smallest. Now if you see that the complete sorted list, so complete sorted list is 4, 10, 10, 13. So this 13 is coming at the 4th position. If you will consider this 4. So because of that, we reduce this K value because we have discarded the element before they are coming before of the recursive call part. So we will get this information, and we can write in a different way. So this is a little bit tricky type of code. Otherwise, we can improve this part. We can ignore this part of things. We can make more easy to understand. So simple concept is that every time we will reduce the half part of the search. So currently the worst case thing is still occur in this quick select also, because in quick sort the worst case complexity was order of n square. Same things for the quick select, the worst case complexity will become a order of n square here also. So how we can improve this? We will move to the next algorithm. This is a median of medians MOM algorithms. How we can find out the better median? That will come in the middle part after the partition process. So that will improve our complexity in the worst case things. So what are the steps of median of mediums is MOM. So first divide L into a block of 5 elements. Okay, this is the first steps. And after that, find the median of each block. So this is just we can find out the median element after sorting each blocks. Okay, and after that we will collect all the medians of each blocks, and then we will perform same find the median of each blocks again. We will repeat this algorithms again. So in this case, if you see the code, so this is the some explanation of proving the median of block medians lies between 3 len of L by 10 and 7 L of so 3 by 10 and 7 by 10 of the elements. So you can see after performing these steps. So okay, I'm taking this example and what are the algorithm is and why the complexity of this is n. I'll explain all these things in MOM. So these are some elements. Four. So how many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So total 15 elements are there. So what we will do, we will take as the input list L. If total number of elements are less than 5, we will perform the sort method here, L dot sort, and directly return the middle element. So after sorting, for example, if we have an element 5, 2, 3, 1, 6. Okay, so we will perform if our elements are less than 5, less than equal to 5, we will directly perform the sort algorithms. So the number of elements are fixed here. Okay, this is 5. So total complexity will become a constant thing. So 5 log 5. Okay, and log n. So same things if we are performing sort operation here. So the n value is now here fixed value 5. So the total of number of operation is become fixed. That will be so we consider this is a constant operation now. This is not dependent on our inputs. So 5 log 5 is the constant value to perform this L dot sort if element are less than equal to 5. So after sorting these things, 1, 2, 3, 5, and 6, we will return the middle element. So that means this is a median element of the our input list. This okay. But what happens if our elements are greater than the 5 elements? So we will perform these things. We will divide the elements in our block of 5 elements. So you can see that these are the sequence of our elements of 15 elements we have. So we will take the first 5 elements. So first 5 element is 4, 3, 5, 6, 2. Okay, these are the fixed value of the elements, 5 value, and we will perform the sort method here. Okay, so after sort methods, so the complexity will become 5 log 5. This is a constant value. Okay, we can consider this is a constant thing. So after sorting, we will get this thing. So 2, 3, 4, 5, 6. I'm writing vertically here, and the second 5 element is here 1, 2, 1, 10. Okay, so 1, 8, 9, 7, 10. So these are the 5 element. Once again, we can perform sort operation on these element in the constant time 5 log 5, and we will get the sorted list 1, 7, 8, 9, and 10. Same we will perform on the next part. This thing. This is also a 5 element. 13, 15, 18, 17, and 11. Okay, then we will perform the sort operation on these 5 elements, and then we will return the middle element. So this will become a 11, 13, 15, and 17, and 18. Okay, so each block we are sorting. After that, we will collect the medians of each block. So median of the first block is 4, next block is 8, and next block is 15. That means we collect these things in our M list, in our code M list, median of medians. So these are the medians. Now we have these element in our list 4, 8, and 15. Now we will call this MOM function on this input list. Now the first base case condition will be satisfied. Now the number of element L is less than equal to 5. So that means number of elements here is 3. So we will perform the sorting operation on that, and we will return the middle element. So after sorting, this will become 4, 8, and 15, and we will return the middle element 8. So it will become a median of medians. So finally we can say that this is, we will select this 8 element as a median element from this list. So you can see if we are performing this operation, median of medians below, so we are sure that our median element will always come after 1/3 element in the sorted list. From the our median element will always come from the after the 1/3 elements after the sorting list. So we can say that this part will always be lesser than our median. Okay, you can see the all value 2, 1, 3, 7, 4. These all value are lesser than this one. So we can say if we are selecting this median of medians element, so definitely this median will lies between 1. So we can say 3/10 to 7/10 range. In this range after sorting elements. So if we have a 10 elements in the sorting, so our median element will become in after third elements. Okay, so we can say, so that means we are not guaranteed that the exact median we are getting here, but that are the closely to median. So we are getting this median information in order of n times, because if you see this code, what will be the complexity of this code, please? Can anyone explain what is the complexity of the overall code is, and what are the region? Anyone can explain what are the complexity of this MOM here? No one? Okay, so complexity we can measure, we can check that. So this is the first case. Here we are just checking, this is the base case actually. Okay, here we are getting if len of L is less than equal to 5, we are performing this L dot sort and return the middle element of the sorting elements. Okay, so here number is fixed 5. Okay, so this part of this block of code is not dependent on our input size, actual input size. If we are, for example, if we are providing this 100 element in our input list L, so this part will remain, this part will perform only for the 5 elements. So we can say that this part is a constant time. So we can assign that this is a order of n time, constant part. The remaining part here, same things. So we are performing a loop for I in range 0 to len of L5. And here we are also performing, finding out this block of 5 elements. Okay, we are finding out the block of 5 elements. That means we are just selecting the 5 element, and we are performing the sorting operation here. So that means same things, we are performing this x dot sort on the 5 elements. This is also a fixed value, that we can say that this is also a constant operation. Okay, so this loop is actually a main loop, and here we are actually performing order of n operation. You can see that inside this operation we are performing each operation as a constant operation. This is also a part of, we can see that this is also a constant part, and this appending is also a constant part. Okay, so inside this for loop we are performing each operation as a constant operation. So because of that, overall complexity is order of n. So that means we are finding out the median element in order of n times. So we are not increasing our complexity to finding out the median elements. And same MOM, this function we will use to finding a selection of the pivot element in quick select as well as the quick sort. Okay, so if you see the code of quick select and quick sort things, so if we will move to the previous code, so here we are just selecting these things. So we know that this part, this is called a partition process, this is called a partition process, and we are performing this for loop here, and it is taking order of n times. So we can see that the partition function takes order of n times. So same things if we are performing serially operations. So we here now we will select the pivot element equal to MOM of L. So that means we are just performing a one MOM operation to select the pivot element. So that is a separate order of n operations. So it is not increasing the complexity of our quick select algorithm, but so the pivot element we will select using the MOM algorithm. So it will mostly come. We cannot say the exactly come in between after the partition process, but it will come definitely after 1/3 elements. It will come after 1/3 elements. Then so that will improve the complexity of overall. That means worst case we are improving here. So worst case, what was the condition of worst case is if every time pivot element come at the first position, but this situation will not be happen using this MOM operation. So we will replace this pivot selection. Here we are selecting the first element as a pivot, but in the fast select algorithm. So this is the MOM algorithm. We are performing this task in order of n times. So this is the fast select using MOM. So here the change only is that we are just selecting this pivot element using this MOM algorithms. Okay, so this part is also taking a order of n time, but it is a separate. This is not coming in any loop. So this part will also take order of n times. After that, we will perform our partition process. After some modification, we will perform our partition process, and we will return the exact position of our pivot element. And so we can improve our worst case complexity using this MOM operation if we are using this MOM. So it will return. So we are calling it as a fast select, because here we are improving our worst case situation. So any query in this fast select and quick select and MOM? Any query? MOM is clear?
Yes, sir.
Okay. And so fast select is basically just improvement using this MOM algorithms. So partition process we will also okay, so we are performing swapping operation, I think. Yes. So after selection the pivot element, we will just swap the position of the pivot element. We are just shifted this pivot element at the first position. Then we will perform the same partition process, and we will find out the small k, the smallest and largest. So same MOM algorithm we can use in the quick sort algorithms, and we can also improve the complexity of quick sort algorithm in worst case. So these are the algorithms where we are improving our complexity using the divide and conquer approach. Now the recursion tree, basically this is a approach to find out the complexity of the recursive based algorithms. Okay, so because of that we call this as a recursion tree. And so there is a difficult, sometimes very difficult expression is created. So for if you have seen that, so expression, I think I didn't explain. Okay, one second. Yeah. So if you see that the Kuratsuva algorithms, Yeah, so this is the Recursive algorithms. So we got some recurrence relation. After that, we expand this recurrence relation by putting the value each time. So after that, we finalize the solution by mathematically things by solving this expression. So this is a little bit difficult. It is become a little bit difficult sometimes when our expression is very difficult. So we can also solve, we can also find out the complexity for this type of recurrence relation using this recursion tree easily. So what are the process, how we can draw the recurrence tree? Yeah. So yeah. Divide and conquer involve breaking. So this is the definition and divide and conquer. Every time we divide the problems into a disjoint sub problems and we solve each problem separately without interfering to each others. And after that, we merge the solution of each sub problem to get the final solution. So complexity Tn is expressed as a recurrence. We can represent the recursive solution as a recurrence relation. Like this. So you can see that the binary search. So binary search, okay, I'll explain once again how we can represent the tree. Okay, so you have already learned many recursive algorithms. So first is binary search. So in same binary search, we always find out the middle element and check that our middle element is a searching element or not. If our middle element searching is not a searching element, then we'll check, compare the element value. If our searching element value is lesser than the middle element value, then we will discard the upper part. If our searching element value is greater than the middle element value, we discard the lower part. So every time we discard the half of the searching area. So initially, we start from the n element, and every time we discard the half part, and we call this binary search algorithm on the half of the element. And in this at the time of this division, we perform one operation to compare, so the one constant operation to compare the middle elements. So we can write this middle value fn value as a 1 plus 1. This is the constant operation required to find out the middle element and comparing the middle element. So these are some fixed operations. So we can perform this value as a 1 here. So you can see that every time we are starting from the binary search on n element, and we are just recursively call on n by 2 elements in the next part. And every time apart from this recursive call, we are performing fixed constant operation. So we can draw the tree. So there is a simple one child. So recurrence tree is like a similar normal tree. We cannot say that this is a binary tree. This can be a normal tree. So any number of childs can be have in this tree. So in this tree, so for binary search, we can create. So in binary search things, Tn in next level. So this is the first level when we call this binary search at the n element, and number of operations is required 1. In next time, we discard the half of the element. The number of elements become n by 2. And apart from that, one constant, so constant operation is required. So we write as a 1. Same things next time, t n by 2 1. Okay, so sorry, n by 4. Okay, similarly we will reach at the base case of 1. Okay, so how many number of levels required? You can say every time we are dividing the element by 2. So initially the total number of elements are n, then we are dividing by 2, then dividing by 2 again, then so we will reach from n to 1 in log n step. Okay, so that means we can say that the total number of level is log n. Okay, yes, and each level we are performing one constant operation. We can directly multiply this fn into this total number of levels. So 1 into log n. So total complexity will become order of log n. Log n. So this is for binary search. Apart from that, for the merge sort and quick sort, we also use the recursive solution. So what will be the recurrence relation for merge sort? So we can write Tn. Okay, every time in the merge sort, this is a fixed divide and conquer things. So every time we divide the input list into two parts, left part and right part, and we call the merge sort algorithm on each part. We did not discard. We will not discard anything. So so we are starting from the Tn, and every time we will perform a merge sort on each part, left part and right part. So we that means we will call this merge sort algorithm 2 times, and each parts contains the n by 2 elements. So this part is we can say this is a recursive calling part. Apart from that, we will perform the merge function. There is one merge function in merge sort, and this merge function takes order of n times. Okay, so that merge function is basically used to merging two sorted array. So we can say that this takes order of n times. So this is the recurrence relation of merge sort. And then how we can derive this using a recurrence tree. So we just start like this. So this is n, then this is, we can say that this is Tn, and then now Tn by 2, and we will divide Tn by 2. Okay, so this is a one problem. We divide this problem into two problems, Tn by 2, Tn by 2, and every time so initial this phase, apart from this divide things, other operation takes order of n time. Okay, so we are just writing a n. So total number of n operation is required apart from that this divide process. Same things for this. For example, if we are performing our merge sort on n by 2 elements, so that means apart from this total n by 2 operation is required at this problem. This is we can see that this is a problem. Same for the this second subproblem. So we can see that n by 2 operation is required for this second subproblem. Okay, if we add all these n by 2 plus n by 2, that means n by 2 plus n by 2, it will become n at each level. So this is the level 0. We can say this is the first level, and this is the second level. Once again, we will call the this divide and conquer operation once again n by 4. Okay, so we can draw this recurrence tree n by 4. Okay, so now this is also a sub problem. We are performing merge sort on n by 4 element. So apart from this recursive call, we will also perform our merge function. So it will take n times. So here number of input size is n by 4. So we can see that our extra operation is required n by 4. So we can say that this will also take n by 4 extra operation. So this is also n by 4 operation, n by 4 operation, and n by 4 operation. Okay, if we will add all the operation at this level, it will also become n. Okay, so this will increase below like this, and at each level total number of operation is required n. That means this number of n value is not a change. Number of operation at each level is not changing. Okay, that is equal. And what would be the height of this tree is, so we can see that every time we are dividing total number of n element by 2, so we can total number of log n level is required to reach at the base case T1. Okay, so we can see that at each level n number of operation is required, and there are total log n levels. So we can say that total number of operation is n into log n. Okay, this is a simple calculation we can do. Otherwise, there are some calculation ways are explained in the lecture. We can directly use this formula to find out this information. So number of operation at each level is decreasing and or equal or increasing. So on these three information, after draw the recurrence tree, you can see that the total number of operation at each level is decreasing, increasing, or equal. On these three information, we can directly calculate the complexity and directly deter. Okay, so this is for the merge sort, same for the quick sort. So in quick sort, will for the best case, the same tree will be created, where the partition function takes order of n times. At each level, this partition function will so total number of operation at each level will remain same n. But in the worst case situation, this tree will become different. So for the worst case situation, for the quick sort, so initially we are starting from Tn, then we will perform the next operation on n-1, then n-2, like this. So this tree will like this n by 3. So total number of operation n, now n-1, now n-2. So the number of level will become n here. Okay, and then we can add these series. So n plus n-1 plus dot dot dot. So it will become n square. So this is the worst case situation thing. Now, if you see the slides, so sir explain these things. Merge sort Tn, this is the recurrence relation, and this is the complexity. And for integer multiplication, you have already seen the naive divide and conquer approach. So this is the recurrence relation for naive divide and conquer approach, where we were calling 4 times on n by 2 elements, plus n number of operation is required at extra cost, as a extra cost. Okay, so how we can draw the tree for this like this? So Tn 4 n by 2, and how we can check that the number of operation is increasing, decreasing, or equal. So now the recurrence relation is Tn equal to 4T n by 2 plus n. So basically in the equation form, we denote this as a C and this as a R. Okay, and this is a Fn. Now we draw the recurrence tree for this is, so we will start from the Tn. Okay, now we will, so there are 4 recursive call here. Okay, so we will create a 4th child for that. So now 1 T n by 2, T n by 2, T n by 2, and T n by 2. Okay, total 4 child is required. So when the input is n, the total number of extra operation is required n. Okay, now the number of input is n by 2 for this sub problem. So number of operation is required n by 2 for this. Okay, same for this one. Number of operation is required n by 2. Number of operation is required n by 2. Number of operation is required for this sub problem is n by 2. If you will add this at this level, so n by 2 plus n by 2 plus n by 2 plus n by 2, it becomes 4n by 2. That means 2n. Okay, same things for each child. Okay, so total 4 subchild is attached with at the same. Okay, and every subchild will contain n by 4 now. N by 4. Okay, so now the total number of operation is required, and so total childs are at this level is 16 into n by 4. So we can see that this is 4n. Okay, you can see that this number of operation are increased. So here 2 to the power 0, sorry, 2 to the power, we can see that this is 2 to the power 0 into n plus 2 to the power 1 into n plus 2 to the power 2 into n, like this. So here total number of operation are increasing in the multiplication way. So in that case, what will be the complexity? So all 3 situations we have already seen. There is one situation for the binary search. You can see that every time number of steps are decreasing. Not the binary search, sorry, fast select. If we draw the tree for fast select, Okay, so what are the recurrence relation for fast select is? So fast select recurrence relation is Tn equal to Tn by 2 plus n. In binary search, we are taking this as a 1. But in the fast select, because we are using the partition algorithms, so this partition algorithm takes order of n times. So if we draw the recurrence tree for fast select or quick select algorithms, so it will become like this: T and the one for level. The next level we are performing on the n by 2. Next is T n by 4, and next thing T n. So at any time we will reach at 1 position. So here the extra operation. So this is the extra operation n when we are performing our quick select or fast select on n input. So that means this is n operation at this level. Now we are performing quick select on n by 2 with the n by 2 elements. So it will total number of operation is required n by 2. Now here n by 4 like this, by 8 n by n equal to 1. So total number of operation at each level is now decreasing here. So there are three situations when we are drawing the recurrence relation, recurrence tree using the recurrence relation. So we can measure these things. The total number of operation are whether the total number of operation is increasing, decreasing, or equal. So you can see in the fast select, quick select type of algorithms, the number of operation are decreasing. In merge sort, quick select, you can see the total number of operation at each level were equal. And for Karasuva algorithms, integer multiplication algorithm, you can see that the total number of operation are increasing, n, 2, n, 4, n, like this. Okay.
Sir, can you explain what is that big of n? Like in the merge sort you have wrote now. In the merge sort, it's like 2Tn by 2 plus big of n. So what is the meaning of that big of n?
This is the
If
extra
at the-
cost. This is the extra cost required apart from this division process.
Sir, this extra cost is like in
This
each and
is
every
due to
step
this
which
is
when we merge it.
yeah, this is due to merge operation.
Okay, so sir, now you said in this merge sort in each and every operation, it's like that big of n is n, like है ना? And in that thing when you divided that t of n into n by 2, n by 2, n by 2, n by 2, and it's like exploding in each and every step. So there big of n is like variable. In each
Yeah,
and every
so
step.
here actually the input is n. Okay, because of that we are writing is n. So we are writing this n just related to this input size n. If our input size is n by 2, then we will write the big O n by 2. Because here our input is changing, input size is changing. Because of that, I'm just writing this n by 2. Number of operation is n by 2.
Okay, so the example just like below this one, what will be the big of n for that? The example just below that, this thing.
This one?
There, below this, below merge sort, in the next page, sir. Just scroll it down a bit, sir. And a bit. Sir, this one. Where you said, okay, it's like 2n, then 4n, then it's like 8n. Something was going on. Yes, above this. Just above this, sir. Yes, sir, this one. What will the big of n in this case?
Big O of n is this. So the recurrence relation, you can see this is a n, and you can also write is big O of n here in our main function. Actually, in recurrence relation, we can write like this 40 n by 2 plus n. So this represent a number of operation, and we can also replace this as a order of n. This is represent as a complexity of this part, extra part.
So, but in each and every operation, this n is changing. But like in the first step, this n is n. In the second step, this n is 2n. In the third step, it
in
will
the
become 4n.
second step, so okay, so in the second level, okay, you can see
Yes,
that this is a problem. Just consider it only. This is
Okay,
a
sir.
sub problem T n by 2. Okay, what will be the recurrence of this n by 2? Now input side we have changed. Okay,
Yes,
now
sir.
just replace everywhere where we are using n, just replace by n by 2. Okay.
Okay,
so
sir. Okay, I got it. Got it, sir.
Become 4n by 4 and this plus n by 2, like this. So this is the extra cost
And
is
then
required.
we will multiply the whole with 4
Yeah.
because it's like 4 steps are there. Like it is divided into 4 equal parts. Okay, sir.
Yeah.
Got it, sir.
Okay, so because of here we are just counting total number of operation at each level. Okay, so our input size is n by 2, we will consider the number of operation as n by 2, same. So this is the step. So you can draw the recurrence tree using this information, and after that you can just find out the order of the total number of operation at each level is decreasing or increasing or equal. So using this information, sir explained some formula in the recurrence tree. So you can directly write the complexity. So these are the last some steps.
And so actually I have a doubt in that formula. So that formula is log of r to the base c. So sir, does that formula include that merge complexity also, or it's like just the formula for
So no,
each and every step
when
levels?
the number of operation are increasing, then we are using this n log cr. If our
Okay,
number
sir.
of operation is equal, so like merge sort or quick sort, you have already seen that the number of operation at each level are equal, n. At that time, we can directly written this fn into log n.
Okay, sir. Got
Okay,
it, sir.
so
Yes.
it become a n log n. So
Yes, sir.
at the case of Karasuba, so at the case of Karasuba algorithms, where the number of steps are increasing exponentially. Okay, so at
Okay.
this at that time we can use this formula n log cr. So what is the value of c? What is the value of r? We can I have written in the page. So basically we represent this. So where is it? Yeah, this how much time we are just dividing the problem. Okay, how much time we are just calling the recursive. So that value is called the c. And what are the input size we are dividing each time each for each sub problem. So we are dividing by 2. So that value will become r. And using this c, r, and fn, you can directly put these things in our formula, and you can find out the complexity. So recurrence using this recurrence relation. Okay, so this is basically formula when our number of operation are increasing. Otherwise, our number of operation is decreasing. You can directly return the complexity as order of n. Like a binary, not a binary search, like a fast select and quick select. Okay, so
Okay, sir.
yeah, so these are the three final conclusion. Actually, these are the final conclusion. You can remember these things, these information, and just if any time you get any recurrence relation for any algorithm, just create a recurrence tree and just check that the number of operation are increasing, decreasing, or equal at the each level or not. And after finding out the pattern, so you can directly apply this formula. So this is the simplest way to find out the complexity of the recursive solution based algorithms.
Sir, actually, I have one more doubt, sir. Actually, there was a tree in which the left part was n by 3 and the right part was 2n by 3.
Still, you can just add the total number of operation. So where it is, this one.
Like, so in this one, so in this one, the complexity, how this depth is log 3 by 2n. I didn't got that, sir. Log n to the base 3 by 2. Log n to the base 3 by 2. How's the depth calculated like that, sir? Can you
Okay,
explain,
so
please?
what is that? Okay, 1 second. So which part will complete first and which part will complete late? Actually, this is happened 3 by 2.
So the right one will complete late, I guess, because it's 200.
Okay, 1 second. So Tn is equal to Tn by 3 and T2n by 3. Do these things. Tn equal to Tn by 3 plus T2n by 3 and plus n plus n. So if we draw the diagram, so in the initially Tn, so total number of operation n required. Now Tn by 3. Okay. Here we are dividing this n by 3, and here we are dividing T2n by 3. Okay, so for example, if we are starting from this 9 elements, okay, so 9 element, this part will I think complete first. Okay, so n by 3 it will become 3, and then 3 by 3 will become 1. So that means will be complete at this level. So n by 9. But I think this part will finish late. So the depth will we are considering from this main part. So same thing, we will divide like this. Once again, t. Now put the total number of n equal to 2n by 3. So now t 2n by 9, and this will become t 2 into 2 and 2n by 3 into 3. So 4n by 9. Okay, so become 4n by 9 like this. So actually this part, so left part of the each sub problem will complete first. Before that the right sub part. So we are taking this large value. So if you just put this value below this one, 3 by 2, we can write this like this, n by 3 by 2. Okay, so this is becoming a r, and total times we are calling. So okay, c will become, this is what we are taking now, 3 by 2. Okay, unequal partitions. Quick sort will pivot in the middle element. So unequal partition allow holes. Depth is log 3 and log series is equal to n log n. So yeah, this actually this right part. So every time when we are calling at this part, this will create a largest depth. So we will consider the depth for this part only. Okay, so
Okay,
in,
sir.
in that case, you can just write like this and divided by 3 by 2.
3
We are
by 2.
taking this
Okay, sir.
equal to r. Okay,
Okay,
so
okay,
because of that we are just written as log r. So log r is 3 by 2. It's like this. Okay, so this is the recurrence tree concepts. This is very useful to find out the complexity when you have a recurrence relation. Okay, and other than that, any topics? B8. So any problem in closest pair of points? Anyone? I've already discussed
No,
this
sir.
in the last session. Yes, Weber?
No, sir. No, sir. No, clear, sir.
Okay. So others, if you have any doubt, you can ask. Anyone, if you have any doubt? Or any other discussion, if you want to share some feedback about the course, what you are feeling about the contents, it is difficult and moderate and easy, you want to discuss.
I think, sir, this course like pretty difficult, but it's going like really fast.
Okay,
It
that
should
means
take more than
content is large.
Yes, the thing is, we are not solving enough questions regarding that, and then after that, we are getting next week to solve. Like we are
Okay.
running with this stuff.
So how many
Like I am
subjects you
getting
have
this
taken?
week.
So we are unable to go back and check the previous week the problems like which we are unable to solve. So we are unable to go.
The real problem is like we have to attend the live coding session, then you have to review it, then again you have to like practice problem, graded assignment. So like if we don't solve that, we will not be able to solve this week, and we cannot review the previous week because that thing is gone, then it's gone only.
Okay. So how many subjects you have taken in this term?
So, this time it's like one only. Actually, I was
One.
busy with my college stuff. That's why.
Okay, currently you
But like,
are doing other course also.
yes,
Okay, okay. And yeah, Aja,
is it,
Buraja.
sir,
Yeah,
actually, I
you
have
can
a
call me
doubt,
Raja. Yeah, even I have taken 4 courses actually. So that's why I was unable to go back and check the previous week graded assignment, which I have missed. Maybe I was unable to solve it. So kind of things I couldn't revisit and see where I did the mistake and all I couldn't see.
Oh, okay. So apart from this, in this course, what are you doing currently?
Actually, I'm working from home.
Okay, you are working from. Okay, so currently you are doing job also.
Yeah.
So that way,
so
that.
for me also, like last time I took 4 courses, and this course I wasn't able to clear it, although with good marks. So I have to like repeat this course
Oh,
again.
you have
That's
already
why.
attempted this course in the last term.
Yes, sir, but I didn't got the good marks. Like I repeated because this course is like really important, because like
Yeah.
everyone say, okay, data structure and algorithm is one of the important parts you have should learn. So I repeated it again. Yeah, I have to see what this stuff really is.
So still you are feeling difficulty in this
No,
term.
and now it's fine. Now it's fine. But then also the course is really tough. I know, like
Yeah.
solving many questions really take time.
Okay, that means the. So which part of the course, like the programming part, you are facing difficulty, or conceptual part you are facing difficulty?
That's the programming part only, sir. Like we don't get enough time to like solve enough questions. Like
Solve the
if we
problems.
think 20 or if we like at least 20 questions we should solve from each and every topic, but we don't have that much time. We are able to solve only 5 or 6 questions, I guess six,
Oh,
7, and all and those in the live sessions. That's
okay.
the stuff.
And the conceptual part, is it clear? Is it clear?
Concepts are also pretty clear, sir. Yeah, that's clear, sir.
Okay. And are you participating Coursera also?
Yes, sir. Yes, sir. That only I'm doing. But yeah, because I don't know. That thing is not discussed. I guess it's not discussed anywhere. That's why.
Okay.
We don't have any solution to that thing, sir. Do we have, sir, anywhere I can find the solutions? Because I have solved like there are 4 questions. I solved like 2 or 3, but I don't get.
For Coursera problems, no?
Yes, sir.
Actually, Coursera problems. I think you after deadline, I think you can see the solution, no?
No, sir. Actually, like in the first, second part, I tried that, but the questions only got erased from that part. Like nothing is there. You cannot access that thing again. That's
Okay. Okay, I'll check it with Omkar. So how we can access the solution? I think they are not. They will not share the solution. Otherwise, the solution will appear outside, and anyone can easily work on that.
yes, sir.
They did not share. Yeah. Okay, that is the Coursera things. So how we can improve according to you? So what things we can additionally to improve this course?
I guess the time constant is the thing, like which is
Okay, so that
holding us
is
back, and we cannot do anything regarding that because like a 6-month course is converted into a 3-month course. So like, okay,
So I think
that's
yeah, our operation team are working on that. Maybe from the next year, the semester things will come in the picture, like 6-month semester things.
yes, sir. Because this 3 month is like really running stuff.
Yeah, 3 months is very difficult. Okay. Yeah, Sanjeev. Okay, you are also repeating. Okay, good. So, but the subject is actually very interesting if you give proper time. So, I think mainly the time is the issue only. If you are doing job, if you are doing other course within this course, the time is the most.
Yes, sir. This that thing is like course taking credibility. That thing is 4. No, so like we have that thing 4, but managing 4 courses and that also in the diploma level is really hectic. You have to like all the way concentrated in this stuff to solve everything and to get every stuff clear in your head.
Okay. Yeah, Sanjeev, you want to say something about any feedback? So, what part you are facing difficulty? Sanjeev?
Yes, sir. Am I audible?
Yes, you are audible. So you are also repeating this course. So in the last term, what difficulty you feel, and And in this term, what you are feeling?
Sir, the coding part and the conceptual part both are my
Okay. So currently, apart from this course, what are you doing? Are you doing job or anything else?
no sir. No, sir.
Okay.
Mm.
Okay. So actually, basically in the general course like BTech or others programs, so this subject data structure and algorithms is basically teach as a theoretical thing, like just using algorithms. So because of that, but here we are actually we have included the coding things, implementation things. Because you should aware how we can use this algorithm in the real time problems because of that. But still, yeah, the time is the main factor. Okay, actually we are trying to improve this course because the quiz one result, actually we want to share this thing, so we have got the quiz one result. So still only 61% student pass in this PDSC course this time.
This course is pretty difficult.
Yeah. So in the previous term, the result was good, but this time I don't know why this is decreases. The previous term, 70% student was passed in the quiz one, but this time only 61%.
So the same thing happened like when I was like at the edge of clearing the term tool. So that time I took the course English 2, Statistics 2, Mathematics 2, and this programming in Python. So that time also that Statistics 2 and Mathematics 2 like got messed up. So because those two courses are really hectic to manage together.
Yeah, I know the stats 2 result was also poor. So
And the last time I took that course, I took DBMS and this machine learning and business data management and this thing. So like in the end, I like really thought, okay, I cannot do this four stuff together. Otherwise, I will not be able to learn anything. So I concentrated on three, and I thought, okay, this thing I will clear, and I will like again repeat this stuff, this course. Otherwise, I will not get any of this four things. I will be in the middle of something where I am not getting anything.
Okay. Okay, so how we can improve this programming things? Actually, basically, what happened in the program, every question contains their own logic. So this is not a formula-based type of things. So if we teach the formula and then you can apply directly. Every problem you have to think. Every problem you have to find out the logic to solve. So the solving of the programming problem, these things can be improved only by the practice, or by all the main reason you can improve these things only by the practice. Yeah, so because of that we have included many problems. So 3 problems we are given in the graded assignment, 2 in the practice assignment, apart from that 4 or 5 in the live coding session. So yeah, that cannot be so these things cannot be improved in the short periods. So after
Yes, sir,
1
like
year, 2
logic
years,
building takes time, sir.
yeah, logic building takes
Yes.
approx 6 months or 1 year times.
Yeah, that's the stuff.
Yeah. Okay, so
Actually,
just
sir, I have a doubt in one question. If you have time, 5 minutes, then you
yes,
can clear
sir.
that. So in the week 4, there was a last question. Like every stuff, like I'm cleared with every stuff. There was one question that I'm still in doubt, sir. In the week 4, graded
4 graded
yes, sir. In the week
assignment,
4, last graded assignment question.
programming, no?
Last GRP 3, sir. Yes, sir.
Yeah.
In the programming last question. This I am not cleared now till now, sir. I like tried many stuff, but I still am
Oh,
confused.
this is a longest journey.
Yeah, sir. Otherwise, every GRP is clear with me. This thing, like, I'm really in doubt with this. I'm not getting it.
Okay, so I think deadline of this week has already been passed. So you can just share your code.
Yes, sir.
On
That
the,
I
you
didn't
can,
solve only, sir. This Thursday, but I was not getting. So, like, I seen the solution code, and I attended. After that, I attended every live session. But this thing isn't discussed in any of this. because we don't
No,
get time.
yes, yes. So
Like till end we
actually,
are busy with this.
this is a big question, and code is also a solution. Code is also a big. So can you say, okay, so you want to just understand the solution?
What will be the approach? Then I will like iterate the code one by my own self, but I want to like see what will the approach toward this thing, like how the code should proceed. That's the thing, sir.
Okay, okay. Yeah. So basically, what we are longest path list. So you have already learned this the DAG things, huh? DAG.
Yes, sir. Yes, sir. Yes, sir.
Directed acyclic grid. So basically, this we are performing this longest path list on the DAG here, and in the DAG things, we are just finding out the longest path length. So okay, so it will take actually one by one. We have to discuss these things. Okay, so can you post this information, which exact part you are facing difficulty to understand on the discourse? So I will reply on that in the detail.
Okay, sir. So I will post it
Because I
on
have
the
to go,
Discord.
because I have to go through line by line this time also, because code is very difficult. Okay, so 1 second. Let's see it. So first, this is a queue. This is the external thing. This is the D inversion. So dictionary inversion for D, which has list as a value. Okay, this is the separate operations. And this is the main operation, longest path function from the lecture. Oh, okay, yeah. So this is the part which I have already used in the lecture. And this is the main function, longest journey. Okay, so L path, longest path, we are getting the longest path from this application, then D list inverse adjacent list path. Okay, so I think in the next session we will discuss, I think, because I have also seen the flow of the code. I think it will
Okay,
be.
sir. Yes, sir. Sure, sir.
So can you give a detailed note in the discourse on pre-order, in-order, and post-order DFS?
Pre-order, post-order, and
In order, no?
in order for BFS or
DFS, depth first search, right? It's part of.
So
I
there is
think.
no pre-order, post-order things. There is one counting things now where we are just assigning this pre and post counting.
In the node, it says, no, first you take left order, then root, and then right.
So that is come in the tree.
Yeah, that was I'm saying pre-order,
Okay,
post-order.
pre-order, post. Okay, I'm just explaining. So, for example, we have a tree like this. So A, B, C, like okay. So for example, we can also A at G H, so G H 5. Okay, so we, for example, we have this binary tree, and we want to perform the ordering thing. So actually, pre-order, in-order, and post-order, all these three are the traversing algorithms. So this is the way to how we can traverse the algorithm, traverse the tree. This is the way actually. So in order traversal, in order, so we actually the way to traverse each node is first we visit the left node. So the only 3 steps algorithm actually. Actually we perform this algorithm recursively. Left node we will traverse first. So I'm just writing traverse left. Left child, and then we will traverse the node in between. In order process, we will traverse we can just add the print node and traverse the right child. So this is the left child, we can add this child, and the traverse the right child. Okay, so these are the recursive part, and this is the simple statement. Okay, if we are starting this in order traversal from any nodes. So for example, if we are starting from the root node, we will traverse our nodes in that manner. We will first recursively call this traversing algorithm on the left child. Then in the next step, we will print the node, and then we will recursively call this traversing algorithm on the right child. This is the, so you can just remember these three steps for in order. And what is the change in the pre-order things? Pre-order things, that means term we are using pre. So that means we will traverse the node first, then we will call the recursive algorithm on left child and then right child. So here actually we are traversing, and in the first step we are just calling the recursively on the left child. Here we are calling the recursively on the left child. So this is the part where we are actually traversing the node. So for the pre-order in the pre-order traversal, just traverse the node first. So we can write the print step first, and after that we recursively call on the left child on the left, and recursively call on the right. So that means if we shifted this print step before the recursively call on the left child, that will become a pre-order traversal. Same for the post-order traversal. Post-order traversal. If we shifted this print statement after all recursive calls. So first we are called recursively on the left and recursively on the right child, and then we are traversing the current node. Print node. Okay, so these are the basic steps of the each algorithm. In order algorithms, we are just going to the left child. Then if there is no left or right child available, then we will perform the print or node operation. Then we will call the we will call this traversing algorithm on the right child. So these are the three steps for in order. If we perform this print operation before this recursive call, then it become a pre-order traversal. If we perform this print operation after that the recursive calls, all recursive calls, it become a post-order traversal. Okay, so these are the steps. After that, how we can traverse the tree. So I'm again we are just drawing the tree and then perform all the traversing. A, B, C, D. Okay, so after that for in order traversal, first that in order traversal.
So pre-order is just like DFS, right?
Pre-order, 1 second. So in
Okay, we'll complete.
no, okay, so DFS, what we will do in DFS. So we just move to the next, okay. Yeah, so in DFS we are also calling it as a recursively, but we cannot say that that is a pre-order traversal. That is the different things. We recursively call until we reach at the end point, then we come back again. So same things pre-order. Yes, you are correct. Pre-order. So in DFS, when we are traversing the DFS, so we perform the pre-order like things. So in order things. So for example, so I have written these three steps. So I'm just written this three step L. That means this L is represented recursive call on the left child, and that P. This is a print step, and this is a R. This is a recursive step. So you can consider that these three steps as L is a recursive step and R is a recursive step, and this P is a simple print step. L means we will move to the left child and we will call these algorithms on the left child. So this is a three steps of any algorithms, and we are performing these three steps on our node A. Okay, so for example, if we are performing these recursive algorithms on our binary tree, so this first step is a recursive steps. So that means we will call on the left child and then we will perform complete algorithm on our left child. So that means we will shift it here on the left child is available. So that means L, P, R. These three steps we will perform on our left child. Okay, now the first step we have completed on the previous node. Now we recursively call on the left child. Now same things, the first step of this part, this recursive call is left recursive call. Okay, when this step will be performed, we will check that is there any left child is available. Yes, so we will shift, we will move to the left child again, L and P R. Now we will perform the first step at this moment. So there is no child at the left position. That means this step will become there is no effect of this step. Now second step will be performed after that, P, that will print the current node information. Okay, this D. So that means D element will be printed first. Then third step will be printed. This is a recursive call on the right child, but there is a no right child is available. That means all three steps is completed. Then after completed of this step, we will return back where we are coming from. Okay, so here we are coming from. After completion this process, we will return back, and so this L call is completed. Now we will perform the second step, print step. Now this B element will be printed. Okay, now we will call at the right things, and that means we will call this algorithm on the right child. So right child is available, then we will perform this LPR. Now we will perform first step, then there is left child is available. Now we will come here, LPR. So now there is no left, then second operation will be performed, P, that is print operation. That means H will be printed, and the right operation we will perform recursively. So there is no right, so this operation, all operation will be completed. Now we will come back to the previous position. So now the second operation, P, will be printed E. Okay, then now the right recursive call. So at the right recursive call, we will move to the right child. So LPR. So there is no left, then we will perform the print operation. This is a I, and there is no right child. So all part is completed. Now we will move to the back. So this all part is completed. Now we'll move to the back. Now all step of this part is completed. Now we will move to the back on the root node. So that is the second step is P. That is A is printed. Okay, now the R part, we will move to the right child, so LPR. Now the first step is left, then we will move to the left part, so LPR. There is no left. Now P, this is F, and there is no right. So for the recursive, all step is completed. Now the P thing C, and we will move to the R part, so LPR. So there is no left. Now print G. There is no right. So yeah, so this is an in-order traversal sequence. If we will perform the in-order traversal sequence on the binary tree, so this order will be printed. Okay, and if we want to perform the pre-order things, so we will just change the one step. We will consider this P step before the L. Okay, so for every phase, so for the pre-steps things, so for example pre-order, so we will consider that this one. So how recursive actually working? So A, B, C, D, R. Okay, so for the pre-order things, so we will just apply this P, L, and R. That means we will perform the print operation, print the current node information, then left recursive call, then right recursive call every time. Okay, so we will perform first step, then that means A will be printed, and after that the second step is the left recursive call. We will move to the left child if it is available. So P, L, R. So same things, the B will be printed here. Now left, P, L, R. So now P is here. Now D will be printed. Now left, there is no left, there is no right. Then we will move to the back. Now right part is there. So P, L, R. So P. Okay, so E is printed. Now left is so P, L, R. Now this one also H is printed. Now there's no right. all part is completed. Now left part is completed. Now right, P, L, R, so print I per I is printed. Now all left completed. Now we will move to the this right part. So P, L, R, so this P, C printed. Now left, now F printed. P, L, R, all completed. Now right, G printed. So in the pre-order traversal, we will perform this type of information, access the node information first, then we will check the left child. If it is available, then we will recursively call on the left child, then we will perform this type of thing. So we will get this order. So in this pre-order things, the root node will always come at the first position. Same things for the post. So post order, we will just change this step like this, L, R, P. That means we will traverse the node information at the last. So L, R, P. So we will get the another order. In that order, the last node traverse node will be a root node. So these are the traversing way of these are the way of the traversing of the tree. We can traverse using this concept. So yeah, yes, you are correct. In the DFS, basically we are performing this pre-order type things. So every time we traverse the node first, then we will move to the adjacent nodes in the graph until when we will reach at the last node. So, but in the graph there is no left or right child is available. So adjust can be anything. Any number of edges can be available in the graph things. So there is no this type of information of left child or right child for the pre-order in order traversal. So basically this terminology used for the tree traversing. Pre-order, in order, and post-order traversal. Basically this terminology used for the tree traversal algorithms, not for the graph. So these are actually there are lots of questions are also possible of these input in these things in order, pre-order, and post-order, but that are not in the syllabus. So because of that, this part is not in the details of the big 6.
Okay, sir. One graded assignment is there. That's why I think.
So I think that is related to the binary search.
Okay.
Actually, if you, for example, if we have given the pre-order things, so I think you are saying that one pre-order is given, and we are asking that something related to this. Okay, do you remember the what in which week the question is?
Week 7, I think.
Week 7. Okay, week 7 is also a binary search related topics are there. So okay, graded assignments theory.
GRPA 1 or 2 or 3.
Okay, this is AVL tree.
No, sir, GRPA mein.
Oh, programming. Okay.
Yeah,
These things.
yes,
Yeah, actually in the suffix code we are performing this traversal. In AVL tree, we are just traversing the tree in the all way. In order traversal, pre-order traversal, and post-order traversal. So same algorithm we are using here. If you see the solution, I think the suffix code is not available for you. Yeah. So here actually, if you see, solution is available. So you can see the code for this in order, pre-order, and post-order. So here actually what in the in order traversal, you can see that we are just performing the left recursive call. Then this is the second part. We are just reading a value, and this is a right recursive call. That means in between we are reading a node value. Before that, we are just calling this in order algorithm on the left part. After that, we are calling a in order traversal on the right part. So this is a in order traversal. If you see the pre-ordered things, so we are first reading a value, then we are just calling recursively this function on the left and the right. And the post-order things, when first we are just calling on the left child this function, and then the right, then in the last step we are reading a value. So these are 3 different way to traverse the tree. pre-order, in order, and post order.
Okay, sir.
Okay, so simple. This is a very small change in all these three. Actually, some if you know that postfix, infix, or this type of things. Do you know? In the expression, in the mathematical expression, we can represent any expression in a infix form. So like this, a plus b. So this is called an infix expression, infix form of any expression. If we write like this, a plus ab, this is called a prefix form of any expression. And if we write like ab plus, this is called a postfix expression. If you know
In
this.
count, we use count normally, count plus.
Yeah, no, this is not a count things. Actually, this is an expression, mathematical expression, a plus b. So this is the form in, we say that infix form. Generally, we use this type of form. But how the computer solve this expression? Computer solve the expression either in this way or either in this way, after converting this expression into this form of things. So if you write the any expression like this 2 plus 3 into 4, after that minus 7 into 3, like this. So if you are writing any expression in the compiler or in the editor, so how they can solve this type of expression, which part solve first and which part will be solved second, like things. So basically in the compiler, this is called the infix expression. We, as compiler, convert this expression into a postfix or a prefix expression, then it can be solved easily. So this is the internal things. So this infix, prefix, postfix is the similar things is related to the in order, pre-order, and post order. So if we created any tree for this type of expression, we can directly convert to a prefix and postfix things. So these topics are out of the syllabus. So that actually in the free time we can discuss in details in any session. But these are not covered in the. But you can explore these topics in outside of the resource. This is also a part of the data structure and these things, algorithms things.
Right, sir. Thank you.
Okay. Okay. So if you have any, if you don't have any doubts, so shall be closed. Okay. Thank you, everyone.
Thank you, sir.